All right, so we're going to pick up, essentially we're going to pick up where we left off last time. We were covering, measures of centrality, right? Mean, median, mode. And there was something that I started to touch on that deserves more time, really. And that's this idea of sampling. And we're going to do this a lot throughout this course. We're going to look at a phenomenon that has some sort of random process, and we're going to build some way to sample from that phenomenon. And then we're going to use sampling and maybe double up on sampling in order to gain some kind of surety around a metric, some statistic. So in this case, this was pretty straightforward what happened here, right? From random import choice, and then we're sampling from this range between 0 and 99, right? So we're not including 100. It can be any number between 0 and 99. And we put samples into this list, and then we're simply taking the mean of, we're doing it here on line 165. We're taking the mean of the samples. Now, we only get 5 samples, right? And when we run this, and I'm just going to run this a few times because I think it's important to think about this, especially as we get into measures of spread. Here, we run this summary. So we know what our mean is supposed to be, right? And we could do this with any range. We could, put we could get all the odd numbers or every multiple of 23 or anything like that, and we can see what our mean is supposed to be given our phenomenon, right? And then we can look at where our mean ends up, right, and where our median ends up. And if I run this enough times, we're going to see sort of this spread around the mean. And I think this is a nice way to start thinking about spread, right? So 31.6 or 48.2, right? 55.2. A lot of the time we're getting close to the mean, the actual mean, but we don't really have enough samples. Now, what if we lower this to just 3 samples? I think sometimes it'll be a little surprising how good we actually do. But, we're seeing sort of a widening of that spread, right? Because now we're getting 3 numbers instead of 5. And so the balancing effect of of fewer samples, the balancing effect that taking more samples would have is even more lost when we're taking 3 samples instead of 5. So I think there's some intuition to be garnered there, and we're going to expand on that intuition somewhat today. I think before we get to that, though, there was one last thing, something we didn't touch on from the measures of centrality slides, and that is discrete versus continuous data. So let's talk about that. And just getting my pen set up. Okay. All right. So we have these 2 ideas that we like to keep pretty separate when first introduced. So we have discrete and we have continuous. I'm going to use this word discrete. I'm going to say discretized. I'm going to say discrete. When we're thinking discrete, the way that I like to represent this is we have a number line. And let's say that number line goes from 0 to 9. And so, 1, 2, 3, 4, 5, 6, 7. It's pretty well balanced. And when we're thinking about discrete, we imagine that there is no space between 0 and 1, right? And often a reason that we might do this is that discrete implies countable, right? It's really hard to count from 0 to 9 if you include every grain of precision between those values. 0, 0.0000000000001, 0.0000, like it's going to take forever, right? And that's not even, and that would still be discrete, honestly, because we're not giving it infinite precision. We can't actually count something that has infinite precision, and so by definition, something that is continuous is not actually countable unless we discretize it, right? So, just visually, if we want to think about this, if we're considering the values between 0 and 9, and if we're considering those to be discrete, then we can kind of say, okay, well, these are kind of like blocks, right? We don't have anything between 0 and 1, or we don't have anything between 3 and 4, or 4 and 5, and so on. And so, we can't report 6.37 as a value because there is no 6.37. There's only 7 or 6. And so, we don't have anything in between. And I think thinking about something as being discrete is sort of helpful really in light of the idea of something being continuous. So let's take that same number line and instead go from 0 to 1. Now, we could go 0, 0.1, 0.2, 0.3. We could do that. But let's imagine there's this point right here, okay? And this point is 0.3974221, and let's say I just do that forever. Now, if I give this infinite precision, if I have some way to measure this with infinite precision, then how many values are there between 0 and 1? Can I count that? No, I can't count that. Not only would it take me forever, it's not actually possible, because no matter how precise of a measurement I make here, right? Let's say I have a precise enough tool to make that measurement. Well, it doesn't mean that there isn't a value between 0.3974 and 0.3975, right? There are values in between there. In fact, there's an infinite number of values between there. So when we're talking about continuous, we're thinking about things that we can measure as opposed to things that we can count. And that may seem like a simplification, and it is a little bit, but we can think about this in terms of problems or in terms of phenomena, right? So, name some things that you would count, that you would use a discrete distribution to represent, right? Think about things that we consider in a discrete form. Just throw a couple of things into the Slack. Votes, yeah, we don't necessarily get percentage votes. I don't vote 1.3974273, for somebody. Puppies, yeah, I'm not about to, get a percentage of a puppy or 3.25 kittens. That sounds awful. Eggs, yeah. Often we think about people in this way, right? People, eggs, really anything that we're considering in terms of counting. Now, this doesn't mean that we can't represent these things statistically in a continuous fashion, right? Like if we're talking about the average, right? What's the average number of kittens that people have? It's probably 0.07 kittens, something like that. I don't know, but it is a continuous value. In fact, because we are considering it in terms of being an average. But we can take the mean, the average, and have that be a continuous representation. It is sort of a measurement of the centrality of a discrete or continuous data set. So if we were to count how many kittens everybody has in the country, and divide that by the number of people, we're going to get a fractional kitten, right? We are going to get that. And that we could consider, we likely would consider as a continuous value, although at that point it doesn't really matter, continuous versus discrete. We're just thinking about it as the average. What about continuous things? What are some things that we consider in terms of being continuous data? Yeah, time. Time is really, time's a big one. Color spectrum. See, now this is interesting. It depends on where you are considering the color spectrum, because on a computer, right? On a computer, you represent color discretely, actually. But in our reality, we perceive color in a continuous way. If you can imagine that. Now we can represent color in a pseudo-continuous way, as we do when we measure luminance between 0 and 1 for RGB, let's say, or HSV or anything like that. But in general, on a computer at least, we represent color as being discrete. But in reality, we would assume it to be a continuous phenomenon. Time is an interesting one, because there's still a chance that we're going to find out that time is quantized into discrete packets. The jury's still out on that one, but from everything we perceive at the moment, according to the person who predicted the Higgs boson particle, time seems to be continuous, but there's still a chance that it's discrete. However, for our purposes, we're going to think about it as being continuous for sure. I think time is the quintessential one, right? That's the one. If you want to think about something as being continuous, you can subdivide a moment and divide that again and divide that again, right? And you can divide it to an instant, but there's never an instant that we can measure, right? There's always a further subdivision of time. I think you can do the same thing for any kind of measurement, really, like height. I like to think of this in terms of height, the height of trees in a forest. There aren't going to be any two trees that are the same height unless you discretize your measurement, right? So, maybe you can only operate at a certain level of precision. Maybe, thousandth of a meter or something like that, given your measuring tools. But you can imagine that you have an infinitely precise measuring tool. And if you do, then there's no way that two trees in the universe are going to be the same height, right? Because we're dealing with infinite precision at that point. So if you want to think about it this way, think about continuous in terms of infinite precision. Infinite precision of a measuring tool, measuring implement. And think of discrete, in terms of counting, in terms of packets, in terms of frames, in terms of non-divisible entities. Okay. So that said, let's get that's just finishing up from last week. Let's get into some summary stats. Now, the average, the mean, tells us a lot. It tells us about a central tendency. And like when we think about mean, or we think about especially mean or median, right? We're thinking about, well, what is a potentially representative value here? We can think about mode that in the same way, but we're going to be numeric here. We're not going to try to consider the spread necessarily of categorical data, in terms of mode, because it turns out that we measure the spread of categorical data by first mode, second mode, third mode, fourth mode. We think about the distribution, the count of these specific elements. In a lot of cases, we'll think about spread in that way. But for numeric data, we have a number of ways of thinking about spread. Now, some of these are classical, and some of them are, really common for our purposes. This is classical. 5-number summary is more classical, although I do think it's really helpful, and it's a good coding exercise. So the 5-number summary just has returns 5 values. Returns the minimum value from the data set, Q1, which is at the 25th percentile, or you could say it's the median between the minimum and the median. That's another way to think about it. The median, right, which is just that middle value. Q3, which is you can think of as the median between the median and the maximum, and then the maximum value. So we have all the tools we need to write this function in terms of median, right, which we have defined up here. And you can see that this 5-number summary is based very heavily on the median value, right? So we're getting the median, and then we're getting the median of the median between the minimum and the median, and the median between the median and the maximum. It's confusing to say it that way, but we're going to code it. So we're going to take a little bit of time to code that. We're going to take more than 5 minutes to code this, by the way. And it would behoove you to have this document open, this summary stats.py document, if that's what you've been working on, or your code base from our last stats class. So try to get that open if you don't have it open in front of you. You'll want to have access to this median function. And I will also throw this into the Slack, so that you have it regardless. Okay, so you're going to code a function called 5-number summary, and here I'll just say this 5-number summary. And I'll give you a little bit of starter code here. Just be this 5-number summary. And that is going to take a list. And let's put 7 minutes on the clock for this. And yeah, get started on it. Reference the slides if you need to, and if you feel completely stuck, throw your questions in the Slack, and I'll do my best to answer them in the Slack. So we're down to 2 minutes. If you want 2 more minutes after this, give me a quick thumbs up in the Slack. Okay, I'll tack on 2 more minutes. Okay. Do y'all need 2 more minutes? If you feel like you're getting close and you would like 2 more minutes, throw me a thumbs up. I'm not seeing anybody's solution yet in the thread, so. Oh, there we go. the solution coming in. Okay, so not seeing any thumbs up, so I'm going to go ahead and code out. I'm going to go ahead and code this out, and I'm going to try to do it in a very clear way. So first, let me snag this. And what are we looking for? Set that over here. And let's build this step by step. So we need the min, and that's easy enough to get. We can just get the min of the list, right? And we can use that Python built-in function. We need the max, so that's easy as well. That's just the max of the list. And we also could use the median, so that's easy. We have a median function already defined. Okay, so we've already got 3 of our 5. At this point, we just need to determine whether or not to include the middle value. And what do I mean by that? So let's say we have some numbers. And I'm just going to put them in order in a sorted way so that it just makes it a little bit easier. Oh, not 9, 14. 9, 14, 17, how about that? And 20. Okay. So if we're thinking about this offhand, the first thing we're probably going to do is think about this in order, right? So that we can grab the min, right? Here's the min. Here's the max. Here's the median. And so the only question here might be whether or not we include 9 in our calculation of Q1. There's a couple schools of thought on this. In fact, I had a stats professor who did include the 9. In general, though, you're going to have this be your lower half and this be your upper half. You don't include the median value. And so at that point, we just need to get the median of the median of the lower half, which is 2. There's our Q1, right? And 17, there's our Q3. So that's helpful, right? This is good if we're doing if we have an odd number of values, and then if we have an even number of values, of course, let's say this was 8 and 10 in the middle instead of this 9. Well, then we would include the 8 and the 10 because our median is actually 9, right? So that's the only real difference that we're seeing there. And with that, I'll just finish coding this, and hopefully we'll have a good sense of it. So if the length of the list, modulo 2, if it's odd, right? If mod 2 is 1, then it's an odd length list. Then let's get the lower half. So the lower half is going to be the sorted list, which, why don't I grab that so I don't have to retype it a bunch of times. So this is going to be, I'll just call this sorted list, and that'll just be the sorted version of the list, as you can see there. And we're going to take the lower half of this as being the initial index, right, 0, up until the length of the list divided by 2. And whenever we have division, of course, division returns a float. So we need to wrap this in we need to make that an integer, right? So there's our lower half. We can modify this. I'm just duplicating that line of code. And we're also going to get the upper half, right? The upper half of the values. So this is just going to be the sorted list, and we're going to start. Here. Let's see. and go +1, right? Because we don't want to include that middle value. And we're just going to take that to the end. I could put the length of the list here as our endpoint, but notice that's implicit in this statement. Colon blank is going to be implicit. In fact, I don't need this 0 here. I just put it in there so that it's clear what's going on. And then, so this will work for an odd length list. And from that, and I'll put in more code for the even length list in a second. So Q1 is just going to be the median of the lower half. And Q3 is going to be the median of the upper half. And at the end of all this, we just return the min, Q1, the median, Q3, and the max. So this should work for an odd length list. Let's just make sure that it does before we call this on or before we add in our code for the even length list. Okay, so we need some numbers. I've got some set aside here. In fact, I think we used these above, but if not, we'll just put them here again. Probably a helpful thing to see offhand is the sorted version of our, well, interesting. The sorted version of, I guess I just have to count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, good, okay. The sorted version of A, which is our odd length list. And then we're going to throw A into here and see what happens. Okay. So let's verify this is doing what we expect it to do. Just grab this and blow this up a little bit. All right. So if we're trying to figure out the median, well, that's easy enough to see. We can do that in our reductive approach, right, where we just cut these off the sides, and we can see that 9 is our median. And then if we partition these off, then we can see that 5 is our Q1 and 18 is our Q3, right? So we can see that is working. And obviously our min is 1 and our max is 27. So that is working as expected. Let's throw in the code that will allow us to get the even length list. So I can just put an else in here, and I'm going to modify these. Anyone have a thought offhand how to change this? What would be the best thing for me to do here? Something simple that will work for the even length list. And it's a simple thing I can do on line 186, as it turns out. Well, I am just using else, and there's something I can do, just something very simple I can do to this to modify the upper half. Remember, if it's an even length list, we're going to include all the values. Get rid of the +1. That's exactly right. We're just going to get rid of this +1. Because if it's an even length list, the actual median is, well, the median may not actually be included in the values of the list unless we've got, you know, this a duplicate of 2 middle values, right? Like 9 and then 9, because then the median would be 9, right? But if we have 8 and 10, then the median's 9. 9 is not actually a value in the list. We want to include all the values in the list when we're determining the halves of this. So that should do that. Let's pass in B and see what happens. and I will comment these out. Theoretically, I will comment these out. There we go. All right. So let's really quick verify that this is working correctly. There is a chance that it's not, but I think it probably is. Okay. All right, same reductive approach. We can just cross these out. Wow, that's a lot of numbers. I could have made this a shorter list, but I didn't. Okay, so the median of 16 and 22, yep, that should be 19. So that's looking good. And then if we include these, right, we've got a min of 1, that makes sense, a max of 56, and I'll just change the color here for determining this. So let's look at, so we've got 48 for Q3, and we've got 7 for Q1. So that's working as we'd expect it to work. Now, honestly, this isn't the only way to write this function. There are a lot of ways to write this, but I'm writing it this way to kind of show you that you can piece out the idea, right? Like, look, if you need 5 things and you know what those 5 things are, you can just get them one at a time. You can say, oh, okay, well, my 5-number summary, well, I need the min, I'll just get that first. I need the max, I'll get that next. And you can kind of build your functions in this way. So there is something that we can see in this. And maybe I'll just snag this again just to talk a little bit further about the 5-number summary. We can get a sense of the form of our data, right? We can see, well, how spread out is it, right? Like, arbitrarily, this second list, B, looks more spread out, right? We have a min and a max that are further apart. We have a Q1 and a Q3 that are sitting, fairly wider than our data set A. And I think for that reason, 5-number summary has staying power. You can get a quick idea of numeric data just offhand. Also, the 5-number summary is represented in the box plot, which we're not going to cover in class, but it is in the materials on Learn. Box plots are, I don't want to say they're antiquated. They can be really helpful. We tend to use things called violin plots more often than box plots anymore. But there are a lot of spaces where box plots are just everywhere. And, it's good to have a familiarity with them. You'll build more familiarity with them in the Learn materials and in the DSI itself. But there are a lot of, in most cases, when you think you want to use a box plot, you actually want to use something else. It's sort of like pie charts. Box plots are nice for certain ideas. Also, never use a pie chart if you can help it. But, there are other things than box plots. And we don't use 5-number summary as often as we tend to use other statistics. But I do think it's helpful. And it is at least helpful as a coding exercise. Okay. All right. So let's skip this breakout. In fact, are these the same numbers that we were just looking at? That'd be, good. We already did this breakout. Let's just leave it at that. All right, perfect. So there are some other benefits of the 5-number summary. So we have this idea of IQR, or interquartile range. And if you break that word down, interquartile, right? That's the middle 2 quartiles. It's the space in between Q1 and Q3, interquartile. We will often use IQR in a way that we qualify outliers. And that's how that's a way to think about this. IQR also gives you a sense of the middle of your distribution, which is often what we're considering. So, in this case, if we're considering the IQR, we're considering the spread of data between Q1 and Q3, right? Here's our IQR. Here's where we would expect to see 50% of our data. So in a similar way, not the same, when we're considering a normal distribution, we're often trying to figure out where the bulk of our data is, right? And it's usually in the middle. So IQR kind of has a similar feel to the middle of the normal distribution, you could say. So IQR is very simple to calculate. It's just Q3 minus Q1. It's the value of Q3 minus Q1. In fact, we can look at this, right? The IQR of B is just 48 minus 7, or 41. So how do we use it to qualify outliers? Well, how about this? We don't need 4 minutes to code this function. I'm going to give you the let me give you the solution for the prior function, so you have it. And I'm going to give you 3 minutes to code an IQR function. I'll put a little bit of starter code in this document. So I just put the 5-number summary, this 5-number summary function in the Slack because you're going to use it in your IQR function. So here's the header, IQR, and you're going to pass in a list. Okay, and let me snag this slide, and I'm just going to leave this open up here. I'm going to leave this here as well. Well, yeah, I'll leave that there as well. And I'm going to put these in for our data sets. Okay. And I'll also put those in the Slack. And immediately after I put those in the Slack, I'm going to put 3 minutes on the timer and get to coding. Okay, you're just coding the IQR function, and yeah, go for it. All right, so this is deceptively simple. And let me just show you how this goes. So we need Q1 and Q3 to determine the IQRs. We can see up here. So Q1 and Q3, where do we get Q1 and Q3 from? Well, we just conveniently wrote a function that gets us Q1 and Q3. So we can just use that, and that's what I'm going to do. So I can call 5-number summary on that list. And we don't need the min, right? We don't need, we do need Q1. We don't need the median. We do need Q3. And we don't need the max. So when I call this, this is going to unpack these into these values. I'm going to go ahead and put underscores in for the things we don't need. This is just a Python convention to say, hey, I don't need this. And from this, I can just return Q3 minus Q1. So that should work. And why don't we, let's print A, let's print B, and let's print the IQR of, well, let's print the 5-number summary of both of these as well. So print the 5-number summary of A, and we'll print the IQR of A. I'll just take all of that, and we'll do the same thing for B. And I'll just put a space in between the two. Okay. All right, so if we look at this, let's look at this in context. I'm just going to screenshot this and blow it up. Okay. So notice that the majority of our values in this first data set, or not the majority, but 50% of our values in this first data set are sitting right in here. So really straightforward, easy calculation to make. 40 minus 10 is 30. So that's our IQR. And then similarly, just Q3 minus Q1 in that second data set as well. So what IQR tells us is just, what is the range of 50% of the data? And that range of 50% of the data should sit squarely on the median, right? So we know our median value. We can think how far in each direction, in general, our data tends to stretch. And that can be really helpful. We're going to see a similar thing with variance and standard deviation, although those do have a somewhat different effect. But one of the things that we often will use IQR to do is we'll use it to calculate outliers. So let's think about what this means. If we're determining outliers, and why don't I just do this here? Why don't I do this? Snag this whole thing. And let's just try to think about this in a pen and paper kind of way. So let's do 1, 5, 7, 12, 15, 19, and 30. Right, so there's our data set. A little sloppy, but that's okay. And we can see right away that our median is 12, right? Our Q1 is 5. Our Q3 is 19. So, we can just take 19 minus 5, which gives us 14, and our IQR, unless I made any egregious error, and if I did, please let me know. Our IQR is 14. Now, if we want to determine if a value is an outlier, if we want to decide a value is an outlier by this metric, 1.5 times the IQR, then we can look at the values in this data set and determine if we have any outliers, right? So we could take 1. We can, ask the question, is 1 an outlier? And we can do we can do 14 times 1.5, right, which is 21. And we can go 12 minus 21. And we ask the question, is 1 greater than, is 1 less than, is 1 less than 12 minus 21? No, this is false. So that means that 1 is not an outlier. We can, now if we had a value down here on the low end that's negative 47, right? We could see pretty clearly that negative 47 would be an outlier in this case. So really the question we're asking is if a value in the data set is 1.5 times the IQR lower than Q1. I put the median here. I should have put 5 minus 21. My bad. That's Q1. So if a value is 1.5 times the IQR less than Q1, we can consider it to be an outlier. Is this a hard and fast rule? No. And in fact, we can determine this coefficient. We can determine the outlier coefficient, which I'm going to challenge you to do when we code this. Similarly, if a value is 1.5 times the IQR above Q3, it would be considered an outlier. Right? Is 1,000 an outlier here? Yeah, safely. I think I can safely determine just by looking at this, 19 plus 1.5 times 14, or 19 plus 21 is 1,000 is greater than 19 plus 21. So that would be an outlier. So this is, kind of I'm going to call it kind of a boneheaded procedure. It's not the only way to determine an outlier or to determine if a number is not representative of data that we're looking at. And you don't want to rely on this in and of itself. You want to think about it in consideration of the values that you're looking at, right? Because there can be values where, well, maybe you want, instead of 1.5 times the IQR, you want 1.1 times the IQR or 2.3 times the IQR. If you want to really determine if a numeric value is an outlier, you need to do that in the context of the data you're looking at. So I'm going to leave this up here because I'm going to have you code after the break. Let's take a 5-minute break. And if you want to get started on coding with this before we end our break, feel free. But that's really your call. I definitely recommend taking breaks. But yeah, I'm going to have you code this detect outliers function. So I'm going to put 5 minutes on the clock, not to code the function, but to take a break. And I'll see you all back here in 5 minutes, and we'll code this function. All right. So I'm going to put 4 minutes on the clock, and you're going to code this detect outliers function. So let me go ahead and get you started on that. Notice that I put in a parameter here called outlier coefficient. Now, feel free to just to either ignore this and hard code your outlier calculation with 1.5. That's fine. But if you want this function to be more helpful, then it would be nice to be able to pass in a different value instead of 1.5, 1.75, or 2, or 2.3, or anything like that. So I'm going to put that function in there, and let's see. And I didn't give you any a data set to test, but the essential way to do this is here, right? So if a value in a list is less than 1.5, is less than Q1 minus 1.5 times the IQR, or if that data value is greater than 1.5 times the IQR plus Q3, then it's an outlier. So what should this function return? The function should return a list of the outliers. Okay, that's what the function should return, a list of the outliers. All right, so I'm going to put 4 minutes on. Feel free to ask any questions in the Slack. So this isn't the easiest function to write. And so don't be hard on yourself if you didn't get to a solution in time. I'm going to walk us through a simple implementation of this, and I'm going to talk through it as we go. So here's detect outliers. Let me just center that. Okay. So we're passing in this list, and with our scheme to detect outliers, we're going to need a couple things, right? We're going to need Q1 and Q3 from the 5-number summary. So we can just snag those first. Q1, we don't need the median. We need Q3, and we don't need the max. So this is just our 5-number summary of the list. So we've got that. We also need the IQR, right? Because we're multiplying whatever our coefficient is by the IQR and adding that or subtracting that from Q1 or Q3 and Q1 respectively. So I can use our IQR function for that, IQR of the list. And we can do a simple collector pattern here where we just make a list, an empty list, and we collect any outliers into it. So for each number in our data set, in the list that we pass in, right, we can just check if the number is an outlier, right? So I can say, well, if the number is less than Q1 minus the outlier coefficient, which by default is 1.5, but we want to be able to have that be variable, times the IQR, if that number is less than this, then we assume it's an outlier. So I can just append this to our outliers list. And this isn't a place for an elif or anything like that. It's just a second conditional. So I can do this if the number, it's going to be a very similar statement to the statement above. If the number is greater than Q3 plus the outlier coefficient times the IQR, then we append it to the outliers. And at that point, we should just be able to return the outliers. Okay, so let's test this. Let's think about where we get to with this. So do this, test some outliers, and I'm going to make a list of a range of numbers from 0 to 100. And I am then going to append something that is obviously an outlier. How about 10 million? How about that? And let's also append negative 10,000. So thinking about this, it seems likely, it seems like these should be outliers, right? So let's check. Let's print detect outliers, and we're going to put in this test outliers list, and we'll leave the coefficient, the outlier coefficient, at 1.5. Okay, so that looks like it should work. Oh, greater than, oh, I see. All right. Where did I do that? Oh. List object is not callable. Oh. Let me make sure I am appending and not just trying to call that list like it's a function. There we go. And so, you know, it shouldn't be too much of a surprise that we got these numbers as outliers. You know, what if we want to how big of just offhand spitballing, how big of a outlier coefficient would we need in order to include negative 10,000? Just what do you think about that? Yeah, let's try it with 20. I think 20 should do it. Oh, we're still getting about 25. Really? 100? I guess I wasn't really thinking about this. Wait a minute. There we go. Yeah, I think we could probably pare this down. You know, maybe 300 would work. You know, we could just shoot in the dark until we hit something. But I just want to drive the point home that we're the ones who decide, right? We're the ones who decide what an outlier is, and we do that based on the data. So let me do that. And we'll go ahead and skip. We'll skip this next breakout, where we determine the IQR and best measure of centrality. If you want to go back and do this, and also I'll include it in our notes, but we'll leave this one and move straight into removing outliers. So I'm going to code this just in the interest of time, so we have enough time to spend on variance and standard deviation, because I think those are pretty important. I'm going to write a function called remove outliers, and it's going to take a list as input and return a new list with all values that are not the outliers. So we're going to utilize our prior functions, right? And I'm going to oh, I put that in the wrong spot. Ignore this. I'll fix this slide. I actually meant to put this on the other breakout the other coding breakout that we did earlier. So let's remove outliers. And when we're doing this, we still want to consider this idea of the outlier coefficient. So I will include that when I code this. So here we've got remove outliers, and we'll pass in a list, right? And we're going to set that outlier coefficient. And by default, of course, that's 1.5. So the first thing I can do, since I've got this function, I can just detect the outliers, right? And I get that by passing in the list and the outlier coefficient that we've set. And we get that in this list of outliers. Now, in Python, it's not very expensive in general to just make another data structure. So I could eliminate, if I chose to, I could take the path of eliminating values from our list. But in general, remember, we have this, light prohibition on modifying the input argument, right? So instead, I'm just going to say output, and I'm going to pack this in with any value that is not an outlier. And I can just say for num in list, if the num is not in the outliers, right? This is very, very straightforward, right? We can just append that to the output. Output.append num. Now, what I could have done instead, which would be, arguably a little bit better. I actually don't believe that. I think it would have a similar runtime. I could make a copy of the list and then do output.remove every number that's in our outliers list instead. So instead of traversing list, I could traverse outliers. That would be fine. I'm not going to do that. I'm just going to run through, and anything that's not an outlier, I'm going to go ahead and append it. But I just want to point out there are multiple ways to do this sort of thing. So if you remember the house price data, I'm just going to grab that and throw that in here. And we're going to detect the outlier, or sorry, remove the outliers from this. So print remove outliers, and I'll just pass in these house prices. So let's see if that works. So looking at these numbers, what do you expect? What do you expect to be removed from here? Okay, yeah. At least 1285, and I think 350. 350 kind of looks like an outlier as well. So let's find out. Yeah. So when we remove outliers, we are getting a list back that doesn't have 350 or 1285 in it. So that's... Oh, and 408, actually. Okay. Yeah, we're also removing 408. Cool. So hopefully that function is not too hard to understand. And that's a good question. Would it be preferred? Would the copy method be preferred if you don't want to alter the original list? Yes. Yeah, and we kind of do that all the time. We'll make a duplicate of a data structure, a list or a dictionary or whatever it is, and we'll use the .copy method so that we're not modifying the thing that we passed in. And then when the function returns, we'll just return the new object that we built. So that's a very common paradigm in Python. It's not always what you have to do, right? There's a lot of flexibility in the language. But at this stage, it's better to just think of it as a rule of thumb. You'll be doing other things like anonymous functions later when you get deeper into Python, where instead of actually returning things, you modify something in place. But that's a different paradigm of programming that we're not going to get into here. I do like the reductive approach a little bit more, honestly, like where you would make the copy, because your assumption is that outliers are going to be fewer outliers, right, than there are data values. And so if you have a huge data set with a very, very few outliers, you'd have a better runtime if instead you just ran through the outliers and removed them from your copy list. But either way is appropriate, and this is sort of like a additive approach, and I think the reductive approach is a little nicer here. But and in that case, you would use a copy. Okay. So the other, when we're thinking about spread, right? We've talked about IQR as a metric of spread, right? 5-number summary gives us a sense of the width and the way that a set of data kind of spreads across. There's a really helpful set of metrics that are much more closely related to distance metrics. Let me pull those slides up. Here we go. And those fall into the camp of, well, we're going to think about them as variance and standard deviation. Okay. So variance is gives you a sense of the average squared. Well, it gives you a sense of the average distance between each data point and the mean, which, if you think about it, is sort of fundamentally a little bit different than what we get from the 5-number summary. 5-number summary is pretty much, we don't know how many we don't know how many data points there are if we're just looking at a 5-number summary, we don't really have a strong sense of the average distance between each data point and the mean. We could get a clumping together around Q1 and Q3, right? And that wouldn't really affect our metrics. We could build so many different data sets that look completely different using the 5-number summary. Variance and standard deviation tend to be our go-to, though. And these are very much distance metrics. When we talk about distance metrics, you'll kind of see that that variance and standard deviation have a feeling of distance away from the mean. Okay, so let's see. What do you need to know here? Here we're going to talk again about sample versus population. And when we're thinking about a sample for variance, okay, when we're thinking about a sample, we're going to call that S squared, okay? So if you happen to be working with a population, well, then you can get a parameter that is sigma squared, okay? So why is it S squared and sigma squared, right? S squared is for sample. Sigma squared is for population. Well, we call it S squared because it turns out that standard deviation tends to be much more helpful to us than the variance, okay? So standard deviation, we'll tend to use standard deviation more because it, as you'll see, it's in the units that our data is in, right? Or that our data are in. So when we say variance is S squared, it turns out standard deviation is just S, right? And sigma. So what you might imagine here is that the standard deviation, the standard deviation is equal to the square root of whatever the variance is. And we'll look at this. So let's should have the formula for this right here. Now, here's where we first see a slightly different formula for a population versus a sample. And there's only one difference here, and this difference we can talk about a lot, actually, and it can get pretty interesting. I only want to touch on it here, and if we have a little bit of extra time at the end, maybe I'll kind of get into some weirdness around it. But the only difference here, right, where here we've got our population formula, here we've got our sample formula, the only difference is this n-1. Okay? So let's walk through what this formula is doing, and then we'll talk about why this n-1 is here. Okay, so I'll just shrink these down. All right, so I'm just going to start with the population formula for this. And it is 1 over n. It's the sum of all values from the first value up until the nth value of each data point x sub I. This is the mathematical representation, so we're starting at 1, not 0, as we would in Python. And we're subtracting the mean and squaring. Okay, so I'll just label this a little bit. This is our mean. Oh my gosh. That is not our mean. That is our mean, mu. And x sub I represents each data point, okay? So 1 by 1, we look at each data point. We subtract from that data point, we subtract the mean, then we square it. Why do we square it? Does anybody have a thought as to why we square these values, the result of this operation? Yeah. Yeah, we get rid of negative numbers. Now, this may seem like overkill, right? Like, why don't we just take the absolute value? And that's a good question. There's actually a mean absolute deviation formula that takes the absolute value here instead. But we square it, and that's how we get the variation. That's how we get the variance. So we square the differences between each data point and the mean, and then we sum them all together, and we divide it by the number of data points, right? So this is our summation here, right? That just means sum everything, and then we turn it into an average here, right? This is where we divide by the number of data points. Divide by the number of data points. So this is for a population. And if you think about it, when we have population data, we know everything, right? We have everything. We're not taking any guesses. We're not, we have all the measurements we need. We could just say, this is the mean, right? We can just say, this is the parameter of this population. This is the mean. The mean will never change based on the sample, right? Now, that means that we have only one population variance. We only have one population standard deviation, right? We only have one, okay? And that's because we know everything. We have all the data. The reason why we have a second formula here for the sample is that the reason we have a second formula for a sample variance and why it's a little bit different is that we don't know the population parameters when we're dealing with a sample. We only have statistics. We only have a guess within error bounds. And so, that's why we have this 1 over n minus 1. We call this Bessel's correction. And it's here to account for what I'm going to refer to as bias. So here we're going to account for bias. So why do we need to account for bias? Let's talk about that for just a second before we code this stuff out. So I'll continue putting everything in here. This is just the sum from the first item to the nth item. And of course, we still have this x sub I, right? This is just our input data. Notice instead of subtracting mu, I'm subtracting x bar. And we're squaring that to get rid of the negatives. So if you take a sample, you're going to get x bar. And you're going to do your best, right, to have a representative sample in order to have an x bar that best approximates the population parameter mu, right? So our hope is that x bar is doing great. It's really, that we hit it on the nose, right? That we got it. But the reality is that we didn't. And, we're pretty much never, we're very rarely going to get the population parameter. So rarely that I'm just going to say never because, like I said, it's a continuous value. The mean is a continuous value. So we have this difference. If every time we take a new sample, we get a different mean, right? So if every time we get a different x bar, every time we sample from this data set, from this phenomenon, then we have a constantly moving target. And that means that, if we're thinking about this like a timeline, or a number line, that is, maybe our mean is going to fall here, or maybe it's going to fall here, or maybe it's going to fall here, or maybe it's going to fall here. And if that's the case, and we're considering the difference between each data point and the mean, then we need to account for that extra area, right? So if we're talking, the distance between, like if this is the span of our variance, well, how do we account for that other x bar, right? The best way to do that is just take it all into account and try to guarantee that we are capturing the variance in relation to a variable mean, right? So whether the mean is here, whether the mean is here, if we did this enough times and we took the mean of the mean, right? If we took the mean of the mean and we found that it landed right here, then this would probably be a decent approximation of our population mean, the population parameter for the mean. But in all likelihood, we aren't going to be able to do that. We're not going to be able to endlessly sample from the phenomenon. We just have the data set we have. We already went through the trouble of building a singular sample. So instead, we're going to apply Bessel's correction and just expand our variance. And if you think about it, that's what this is doing, right? 1 over n minus 1 is doing just that. That is expanding. That is expanding the width of our variance. So, that's just some thoughts about sampling. I'm going to keep harping on sampling as we go because we're going to see it in action when we get to distributions. But just as a basis for understanding what this n minus 1 is doing, it's just expanding. It's expanding our variance in order to try to ensure that we are capturing, the variance around the population mean. So that's the goal. All right. So I'm just going to set this up here because I'm going to have you code out these functions. Now, I do want to say this. When we are, so with the mean, when we're sampling, we want to get a mean that best approximates the population mean. That's something we're attempting to do. We're not actually trying to better estimate the population variance by applying Bessel's correction. What we're trying to do is make sure that we include the variance around the mean. It's a subtle point, but I think it's worth saying. So I'm going to have you code the variance function. And I want you to include a parameter that determines whether the data is a sample or population, right? Then that's just going to be a simple Boolean. I'll show that. And you should apply Bessel's correction based on that. So let me give you a little bit of starter code for that. Of course, you're going to find the previously defined mean function to be helpful here, although it is easy enough to just sum data values divided by the length of the list for the mean. But I'm going to encourage you to call on the prior function. You're going to code, well, first you're going to code variance. And if you're feeling up to it and you get the variance function coded in time, then go ahead and also code standard deviation, okay? And I'm going to grant a little more time to code standard deviation after we look at the variance and after we create a basis for understanding how to interpret the variance. Okay, so I'm going to put, well, what was, I think 4 minutes is good. You're just implementing, these functions. Notice the only difference between the two is this n minus 1 versus the n. And yeah, I'll just put 4 minutes on the clock and do your best. Give me a thumbs up if you want 2 more minutes on this. Okay, I'm going to go ahead and put a couple more minutes. All right, I'm going to code through this, and I'll talk through it as we go. And if you're still working on it, and you feel like you're almost there, just keep working on it, and this will be here. Okay, so we need the mean, right? So why don't I get that? Mean underscore, and this is how I tend to do this mean underscore. That, you can call it whatever you want, but I don't want to name collision with the mean function. That's why I'm doing that. And I'll just get the mean of the list. And I'm going to do a simple accumulator. I'm going to show you 2 ways to think about this. You can either do a conditional if it's a sample, right, which by default will be true. If it's a sample, then we can return the total divided by, we need to run a for loop, sorry. So for each item in the list, of course we want to do this. We want to accumulate into the total the item minus the mean, right? This is our x sub I minus the mean. And we want to square that. So that should be pretty straightforward. Maybe I'll rename this. I'll just do I'll call this x sub I in list if we want to match x sub I. And the mean I could call x bar. Yeah, why don't I call it x bar? Then we'll do that. Just to do a more direct translation between the two. So I can do the total divided by the length of our list and apply Bessel's correction. Now I do have to wrap that in parentheses. And in all other cases, if it's a population, we can return the total divided by the length of the list. So cool thing about Python, and this is something we call syntactic sugar, I can instead just return the total divided by the length of the list minus sample. Now, the reason I can do that is that you can add true. And if you add true, that's adding 1. You can subtract true. If you subtract true, you're subtracting 1. If you add false or subtract false, you're adding or subtracting 0. So this statement right here on line 277 eliminates the need for the condition below. So that's going to work. And why don't I just call this function? I'm going to call this on the house prices because we continue to see those, and I think they have some helpful tidbits in there. I'll close that out while I'm at it. Okay, so let's print the sorted version of the house prices just to see things in context, and let's print the variance of the house prices, and we're assuming this is a sample, so I don't need to put that in there. I'm just going to put it in there just to, because I like doing that. I like including the default parameter values depending on the situation. Okay, so here's the thing. How do we interpret this variance? How do we interpret this variance of 64,140? It's the average of the squared distances. Do we think in terms of distance squared? Not usually, right? We usually think in terms of distance, right? You don't think about the square distance to your friend's house or anything like that. You think about the distance to your friend's house. So for that reason, we have, that's going to be my justification for us having a standard deviation function. So we're running down to the wire, so I'm just going to code this. Standard deviation is just the square root of the variance. And that's really convenient because to define this, we can just set these same parameters and then have a simple one-line return of the variance of the list and the sample flag. And I could import square root, which is a better practice than doing this, but I can just take the square root by raising it to the 1/2. So I'll just do that here. And why don't we let's look at these same values with standard deviation. And I think this looks more representative of the average distance between each data point and the mean. Right? That looks roughly okay. 253,000 around each of these. Around the mean, and maybe it would be helpful to actually print the mean. Why don't I do that? So 620.5, right? So right in here. That seems reasonable. Now, what do you think would be helpful in this data set if we wanted to get a clearer story about the average distance between the each data point and the mean? What would be something we could do to this data set? More data. That would be great. Yeah. I think more data would be helpful. And more data, as I made the argument before, in terms of outliers, we don't know necessarily. We don't know if these three values are truly outliers without looking at the data month after month. I mean, maybe these are normally occurring in our data sets, and maybe our mean of 620 is okay. But if we don't know this, and we're assuming that, you know, this is a representative, a fairly representative sample, then we might be tempted to remove outliers here, and get the standard deviation after we remove the outliers. So yeah, part of the takeaway of this of standard deviation is it gives us a measure of spread in the units of our data instead of in the squared units of our data. And for that reason, it's really helpful. Or that's one of the reasons it's very helpful. Okay, so to kind of drive this point home, let's see. There's actually a breakout, which I'm just going to code out right here. It's on the subsequent slide. And that's just, the same data as before. So we already have the answers to a lot of this. So we've got the standard deviation, the variance, so I'll put this down here. And so the questions here are find the variance, find the standard deviation. If we exclude the values that are considered to be outliers, do you think the variance will increase or decrease? What's your thought on that? If we remove those three values, will the variance increase or decrease? Yeah, it's going to decrease, and I think it's pretty clear why, right? We're eliminating the part of the summation, the values in the summation that are most extreme, actually, and so not only are we going to shrink it, we're going to shrink it quite a bit. So why don't I go ahead and show you a quick way to do that. Let's print the mean of this without, here, why don't I do this? I'm going to get the house prices without outliers. I'll call it house prices, no outliers. And this is just going to get, we can just remove outliers from house prices. And next we'll, let's just print that. We'll print the sorted version of the house prices without outliers. And let's print the mean. And we can just call in here, using an F string, house prices no outliers, the mean of that. And we can get the, let's get the variance. And keep in mind, this is the sample variance. And let's get the standard deviation. Okay. And I'm just going to put an extra space or two in here. Okay. So look at how dramatically that changed our variance and our standard deviation. Of course, those are completely related to each other. It also altered our mean, So not only did we remove the extreme values, but our mean became more centralized to the data in question. So not only are we getting rid of the larger distances, we're also kind of evening up the smaller distances, the distances that include distances between the mean and the outlier. Between the mean and values that are not outliers. So we went from a standard deviation of 253 to 46, essentially, right? And this should give you a sense of the power you have to transform data, right? So if you are thinking critically about the data that you're working with, and you want to appropriately appropriately analyze the data that you have in front of you, then you do need to consider what constitutes an outlier, right? An outlier, something that seems like an outlier might not be, right? If we're doing this month after month, and we're seeing this same kind of spread of data where we have things in the 300,000s and we have things in the 1.3 millions and things like that. If you're getting that month after month, you don't want to remove these outliers. And you don't want to have this standard deviation of 46. But if that looks anomalous in light of the greater span of house sales, then yeah, you probably would want to trim those out of your calculations. Cool. So that is lecture for today. The next stats class, we're going to be jumping into set theory from a very Python procedural point of view. I'll do some drawing, but it's going to be a lot of coding. But yeah, feel free to sign off. That's the lecture for today, and I'll stay on about 15 minutes to answer any questions that you might have about this material or about any material, really. Cool. Thank you all so much. Go ahead and